Hi and welcome back. Here's our part 3 on chapter 18 with cross-tabulated counts. So we're going to enter this part 18.3 with chi-squared test of association. So when we're dealing with chi-squared and we're setting up our hypothesis statement and our test statistic and our p-value. So our hypothesis statement, I think everyone's going to really like this one because we're not dealing with means, right? We're not dealing with means here. We're dealing with an expected value versus observed value. Where we get our O and E notate down here, observed versus our expected value. And so since we're not dealing with means, our null hypothesis is just a statement of no difference. So we're going to say there's no association in the population versus. We're going to say that what we're looking at, there is no association. There's nothing different among what we expect versus what we observed. And then our alternative hypothesis is going to state that there is association in the population. There's something there. We just don't know what it is. So it's a little easier of a null and alternative hypothesis statement to state because we're not equaling 0, we're not having mu, we're just saying that there is no association and there is an association, and that is it. That's all we have to do for chi-squared. And then when we get to the next part, so that part's, I think, very easy. The next part, not so much easy, a lot more math involved because we're dealing with something kind of different. So when we're dealing with our test for chi-squared, we have, it looks like an x, but it's a little bit more than x. It's a Greek symbol once again, and it's chi-squared, and it's equal to sigma, which is all cells, and you're going to take the observed value of I minus the expected value of I squared over the expected value of I. Once again, where O is the observed count of cell I, and EI is the expected count in the cell I calculated E. And E is the expected is the row total times the column total divided by the table total. And our degrees of freedom is equal to the row number of rows minus 1 and columns minus 1. Then the p-value, we convert the chi-squared set to a p-value with a table E or software program. So once again, we have a new table in the back of the book, and it's our chi-squared table, and it's the one just after that. Let me show you if I can find it real quick. It's one right after what we were using. There it is. Appendix E is our chi-squared table found on page 555. So it looks a little different than what we have been doing, but the same kind of rules apply where we have a probability. Chi-squared is only in the right tail, right? So because our hypothesis statement isn't not equal to or less than, it's all in the right tail. So we're only doing right tail probability, and that's how the entire table is set up. So we're just looking at the probability in the right tail, which is what we're going to set our alpha level at, and then we look at our degrees of freedom, and then we find our critical value at that point, and it can determine our p-value at that level or less than. So when we do a chi-squared example, here's the data below. Reveals a negative association between smoking and education level, and then so we want to test it. So we state our null hypothesis, no association in the population, versus an association in the population, right? So no association versus an association. And here we determine our, we have our prevalence and our relative risk, remember, so that we have our 12 divided by our 50, and this is how we get our prevalence. And then we can go back and we can determine our relative risk, which is our P sub 2 over P1 proportions that we're looking at here for each of these. So here we have chi-squared expected frequencies. So we have the expected frequencies of E equals the row total times the column total over the table total, okay? So when we have our table here, so I think one thing that might confuse people is when we do this, this is what we observed, right? So this table here is what we observed. This is our O values. And then when we go forward, these is our E. This is our expected frequency. So this table here is our expected values shown here. And when we find our expected values, we take the row total, right, and times by the column total divided by the table total. So so once again, here's your table total, and so we want our row total of 50 divided by the column total of 94 divided by the table total. So that's where we get, and then when we take 50 times 94 divided by 595, you get 8.034. And you do these for all the values, and then you can get your expected row total times column total and table total. So once again, we're doing our 50 over then now the new row or column total divided by total, and then these values get placed in for your expected frequency values. And then we actually get to our whole statistic. So let's look at this again. So remember, it's a chi-squared stat is equal to the sum of our observed value minus expected value squared divided by the expected value. So here, it's going to be a little flipped back and forth. So here we have 12 minus, so this is our observed value, minus our expected value of 8.034 squared divided by 8.304 squared. So once again, let's go back and look at 12 and 8.034. So 12, once again, this is our observed value, right? 12 found here in the very first box. And then when we move forward, we found our expected total, right, which was 50 times 94 divided by 585 equals 8.034, and that value is here. So we're taking our 12, our expected value, to our observed value and plugging into the formulas, and that's how we get these. And we do that for every cell going forward. So here we have 38 minus 41.9662 squared. So here we have our observed value and our expected value. So we observed 38, and then when we went forward, we're expecting 41.966. The way we get that, once again, is our row total times our column total over our table total, and we put all those values in there. And we do this for every line item on there. So you can imagine the bigger the table, the longer this math gets. When it's a shorter table, it's not as bad, but as you can see, a long table, 5x2 table, is going to take some work. And this is what we do for every value. We take the expected, or the observed minus the expected squared divided by the expected value there. And then once we get a value, which are all these, we sum them, right? Because that's what sigma says. Sigma says add them all up, and when we add them all up, we get 13.2. In order to determine our degrees of freedom, we take our rows, so there's 5 rows minus 1, columns, 2 columns minus 1, multiply them out. So we have 4 times 1, which equals 4, so our degree of freedom is 4. So once again, the math isn't something brand new. It's just multiplying and putting in different values, but understanding where the values come from, I think, is the part that is needed to understand. So you have these observed values, which is what you actually collected as your data, and then you have these expected frequencies or expected values here, and when you place them in, you kind of have your whole new chart, and then you're comparing them to each other, and that's what we're doing, right? Think about statistics. Every time we're comparing different groups in different ways. So here we have expected versus observed. Another great example to kind of think about this is a little fuzzy for you is if you had dice. If you're at a casino, we expect a 6-sided dice to roll. Every number has the probability of rolling 1 over 6, right? So that is the expected outcome. So everything is 1, 6, 1, 6, 1, 6, 1, 6 for each value on the die. However, when you roll it, you might get different numbers to pop up, right? Because that's just how probability works. So that the observed is what you would see the actual dice roll. The expected value is knowing that it's supposed to be 1 over 6. And then you can compare and see some really cool things with dice, depending on how the dice is actually created and formed. You can see some interesting things using a chi-squared statistic. So that's just another example showing how you would observe and expected values to each other. So here we have our chi-square test. So we're determining our p-value. So here we have our chi-square is 13.2 with degrees of freedom 4. So if you use table E, you're going to find degrees of freedom 4. You're going to go over to your probability that we're looking for, and then you find the chi-squared values in this row. The bracket 13.2, bracketing values are 11.14 and 13.28. So if you were to look down, find exactly 13, you would see that it's between those p-values, right? So we would say that our p-value is less than 0.025 but greater than 0.01, and we would say it's kind of taking into looking at this with open mind. 13.2 is really close to 13.28, so it's very close to a 0.01. It might be 0.0109, maybe less. And thus, so we'd say that the p-value is between here, depending on the alpha level that we look at. For a thing, if it was alpha level 0.05, we would say that it's significant at that level. We can also say it's significant at 0.025, but not at 0.01. And that is our chi-square. So as you can see here, 0.05, 0.05, it's less than that, so it's significant at that level. So the illustrated example, so here we go, here's like I said, here's the right tail probability of a chi-square distribution. So if you have your chi-squared of 13.2, which is around here, and 13.28 is the right tail probability of 0.01, and 11.14 is 0.025, so our value falls right there, right? So we'd say it's significant between those two values like we stated earlier. There is one more, so there's the Yates continually corrected chi-square statistic. It's two different chi-square statistics are used in practice. You have Pearson's chi-square statistics, which is what we just went over, and then you have Yates chi-square statistic, which formulas are very similar. However, you're adding the absolute value shown here of observed minus expected, and then multiplying it by a negative 1/2 or minus a half. And then square. The continually corrected method produces a smaller chi-square statistic and a larger p-value, and then both of these are used in practice. So both are used, so you just have to know the formulas are very similar. There's a little bit of a difference between them, and once again, if you want to know more about why that is, there's plenty of YouTube videos that cover this. For the purpose of our class, we're going to be using just Pearson's chi-square statistic, so you shouldn't have to use Yates any further, but just for the complete full overview of everything, there is two different methods, and most of the time if you read a journal article, they will state which method they were using, and most of the time they'll explain the reasons why they're using that as well. So moving on to chi-squared. So how chi-squared works is when observed values equal expected values, the chi-square statistic is 0, right? If you observe values are equal to your expected values, chi-squared would be 0, and when the observation minus expected values gets large, the evidence against the null hypothesis mounts. 2, we avoid chi-square tests in small samples. Do not use chi-square tests when more than 20% of the cells have expected values that are less than 5. So we don't like to use it when there's very small sample sizes in general. Like most statistics, you want more samples. The more, the better things that can be done. When you get the chi-squared, continuing for our third, you supplement chi-squares with measures of association. So chi-square statistics do not measure the strength of association. Use descriptive statistics or R's to quantify the strength. So once again, you have Pearson's R to describe correlation and regression with regards to lines. But when we don't have lines and we want to test association, we use chi-square statistics. But they don't measure the strength, right? You have to use relative risk to quantify the strength of it. Chi-squares and z-tests will produce identical p-values. The relationship between the statistics is the square root of chi-square with degree of freedom 1 equals a z-stat. So once again, these all can circle back to each other. When we have a chi-squared value, we can go back to a z-stat with large enough sample sizes, of course, because as our chi-squared sample reaches higher values, the more and more it looks like a normal distribution, which then you can use as z-stat. A35 uses case control samples, so kind of moving on. Yeah, actually I'm going to stop this video here since we just talked about